Do I need a new share or resume? I think the last time resume took me back to the previous one. Well, let's see what resume does. That's what I thought. Took me to the previous one.
Hey, Bob, if I have to log off and come back and catch this, is this be a recorded video that I can watch later?
Yes.
Are you going to be sending a email out the link to that?
Yes, I will.
Okay.
It'll have the link for Dropbox and
Okay.
the link for YouTube.
Okay. Excellent. Okay. Thanks, Bob.
Oh, I hate this thing. What?
Got the first idea. Sampling.
What are you dipping?
A gummy, sour gummy.
Oh, gosh.
He's like.
Okay.
Like. The test of how well it goes with anything.
Okay. Are we seeing the right screen now?
I can see it. It's not full presentation mode. There we go.
Okay.
Now it is.
All right. Okay, so going to try to explain basic electricity. As best I can.
We're missing somebody down there?
That's Ray, who we never heard from. I guess his audio, or he didn't want to talk. So we're going to talk about what are the basic characteristics of electricity. Look at the atomic structure, which is how this actually works as best we know with the current models. Talk about free electrons, charge, voltage, how we measure it, current, how we measure it, a little bit about the difference between direct current and alternating current. I don't know about you, Fire. So what is electricity? One way to define it is the flow of current or energy caused by a potential difference. There's kind of five main characteristics that we look at. One is charge, which is sort of the fundamental part of it. It's the movement of charge, which is what we define as current. And that's how. And then there's debate about whether charge actually carries energy or not. In my view, I can explain how I think it does. We have voltage, which is a force that can it's kind of like water pressure in a water system. Voltage is that equivalent of pressure, which can force or attract charges. We talk about current, which is the flow of the charges, and we measure it in coulombs per second. We talked about coulombs before, of being a whole bunch of elementary charges per second to measure 1 coulomb. Turns out to be, that's how we sort of do capacitance, where if I have 1 volt and I do 1 coulomb for a second, that's equivalent to 1 farad.
How does coulombs per second correlate to ampere?
It is amperes.
Okay. So 1 ampere is 1 coulomb.
1
per second?
ampere is defined as 1 coulomb per second. And 1 amp hour is 1 coulomb for a second. I mean, for an hour, or 3,600, excuse me, coulombs. So, if you have 1 amp flowing for an hour, and you've got an amp hour, which is equivalent to 3,600 coulombs, or a big capacitor. We have resistance, which is defined as the opposition to current flow. And we normally think of it in the DC world, direct current world, but resistance doesn't care about frequency. It's frequency independent. When we get to the AC circuits, then we also worry about reactance and impedance, which are frequency dependent. But the resistance part of that opposition to current is always going to be the same. It doesn't depend on frequency. And then power is just the rate of doing work. So it's the force, or the EMF voltage, times the current, or the coulombs per second. So if we go back to the basic thing, the atom, which some Greeks decided was the smallest thing there was. And I think there's some Greek name, atomos or something, is where it came from. Today we say that it's composed of a nucleus of protons and neutrons, where protons are positive particles, neutrons are neutral particles, and they have electrons in what we call the outer shell, that, depending on your model of the atom, they orbit around it, or it's like a gas field around it. There's different versions. I'm going to explain it with the Bohr model, which is kind of like showing electron orbits, which are different energy levels. There's elementary charge, which is the amount of charge on an electron or a proton. And charge is, the net charge in the universe is 0. So for every positive charge, there's a negative charge, at least in our known universe. And there's an equal number of protons and electrons. As far as we know.
Where'd all the antimatter go?
I don't know. I don't know what antimatter is. Is it just matter with a negative sign? It's beyond the scope of this book. Okay, so there have been different models for atoms, from just a solid sphere to whatever the plum pudding model was, to back in the beginning of the nuclear days, the Bohr model, called the planetary model, and then you've got the Schrodinger quantum model, which we're definitely not going to talk about. In the Bohr model, you see the nucleus surrounded by electrons at different levels. They call them orbits. It's not necessarily true that they rotate around in fixed orbits. There's probability stuff at any particular time. there may be so many of them at this energy level, but we don't really need to know all that. The important thing is the outer shell, we call the valence shell, and it can contain between 1 and 8 electrons.
Is that the shell that parks my car?
If the electron's free. So let's look at a typical silver atom. It's number 47 on the atomic chart. And the main thing is this outer shell, the valence shell, has 1 electron. The reason that's important is metals or conductors have between 1 and 3 valence electrons. If it had 4, like silicon, it would be classed as a semi-metal or a semiconductor. If it had 5 through 8, it will be classed as a non-metal or an insulator. And if it's the 5 to 8 range, it's extremely difficult to separate these outer electrons, which is why they're non-conductors. In a metal, these are easy to remove by just increasing the energy a little bit, hitting it with a UV ray or heating it, or big enough electromotive force attracting it away.
So when does hydrogen become metallic?
I think it is. How many electrons in the outer shell?
1.
Then it's a metal.
We got 1 period, right? Hydrogen, 1 electron, that's it.
So I have, maybe on the next one, I have a chart. We'll see. So
So is hydrogen ever a solid?
I don't know. Is everything a solid at absolute zero? All right.
Good questions.
Well, I think by definition, to be absolute zero, we would have to have no energy, right? I mean, the atoms and electrons are stationary.
That's kind of ideal or whatever, right?
Yeah, I don't know.
Stationary, like real estate.
Okay, so if I have a non-ionized atom, a normal everyday atom, it doesn't have any charge. If I ionize it, which means I'm going to, in most cases, remove an electron, it's going to leave the atom with a positive charge, and we call it a positron. And the electron that was freed from it, we call it a just a negative ion, anion, I think is the term. And the free electrons will have a negative charge. So we still have an equal amount of positive and negative charges, even though we now have a positive atom and a negative electron out there. If I have more than one positive charge, they repel one another. Like magnets, the positive poles of magnets repel, the negative poles repel. The same thing is true with the electrical charges. Negatives repel, the positives repel. Positives and negatives attract one another, just like a magnet.
What Lewinsa, was he a positive pole or a negative pole?
Whom?
What Lewinsa? Oh, come on, you're old enough to remember what Lewinsa.
I think Well, it depended on the subject, but whether he was for or against, which would say whether he was positive or negative. He was a protester. Does that mean he's negative? Okay.
The reference point is what's good for the people.
So, an example, if I have a copper wire that's 1 millimeter in diameter, and I think that's probably around what, 18 gauge or something. I don't know the equivalents because I don't normally deal with millimeter wire sizes, except in some of these little foreign radio things I build. They give you millimeter wire. But if I have a copper wire that's a millimeter in diameter, carrying 100 milliamps of current, well, I think I lost the title there, that the electrons are actually moving at about 0.01 millimeters per second. So even though charges move at the speed of light, actual electron migration through copper wire is very, very slow. So we like to think of, and a lot of these texts and stuff talk about electrons flowing, but it's actually the charge between the electrons and the atoms recombining that's moving. And in the case of explaining conventional current, it's the holes moving in the opposite direction, which are kind of virtual. And I'll try to explain that in another one or two here. The other thing we mentioned was fundamental is charge. And this is just showing if we have two charges that are the same polarity, they're going to repel, the force is going to cause them to repel. And that's part of Coulomb's law, that force law I mentioned earlier, where it's the product of Q1 and Q2 divided by the square of the distance between them, which is how much force there's going to be either pushing them together or separating them. And this force is coming in the case where they're opposite. If I have a charged up object, it's going to produce an electric field if it's a positive charge that is radiating out from it. And again, Coulomb's law is showing what that force would be when you apply, and I forgot to mention there's a constant in there, which is this 9 times 10 to the 9th. If I have these charges moving, like in a wire, then it's what we call current flow, because it's moving of charge, and we measure it in how many charges per second are moving. And we use that right-hand rule to show the direction of the current and which way a magnetic field is created. And in all of these things, it's really a combination of an electrostatic field and an electromagnetic field, which will always be perpendicular to one another. If I have current flowing in these two wires, and it's in the same direction through both wires, then I'm going to have that force, which is going to force those wires together. And there's some experiments which demonstrate that. I might try to set one up sometime where you can just hang two wires loosely and feed parallel current through them, and the wires will actually move together. And you can do, parallel current will move apart. And if you have a serial current opposite directions, they'll actually attract one another and physically move together, provided you got enough current to provide enough force to physically move it. When we talk about the elemental charge, it's again the right-hand rule where the current is on one finger, the other curled fingers is the direction of the magnetic field, which is circular, and the force is your thumb, which is the resulting force of that, which is also called the pointing vector, and it's spelled P-O-Y-N-T after some, I think he was English guy named physicist named Pointing. Just a confusion factor.
Did we name our thumb Yoda or Obi-Wan Kenobi?
Whatever you prefer. When we look at common things, okay, flat plates will have a sheet charge defined by this formula. If we have parallel plates like we'd have in a capacitor, you have this electric field between them. This is the force or the energy there. If we have a line charge or conductor, and we see this kind of cylinder charge around it. Now that seems to be different than a lot of stuff that used to be taught, where it would radiate out. But in the most recent stuff I've read, and I didn't make this chart, somebody else agreed with it, that the field becomes circular in the direction of the flow, of the charge flow. And the magnetic, and since these lines are parallel, the magnetic field is still perpendicular to it because it crosses it in a circle. If it's a spherical surface, then they all radiate out. Just showing some of the differences in fields.
Go back to the slide before.
To throw that one?
Go back one more. So the left-hand rule, the elementary charge left hand, but right hand thing.
The right-hand rule?
Yeah, this one. So you got the force, current, the magnetic field is rotating by, what's this thing you're representing? Magnetic field too? The one with the blue arrow.
Well, yeah,
What's that trying to show?
I think it should be all those are curled because that's the magnetic field is going to curl around in that direction.
So the electrostatic field is perpendicular to the magnetic field.
Yes.
So
But even if it's in parallel with the conductor, since the magnetic field is going this way, they're orthogonal.
So in this one, how would you represent a electrostatic field or even on a single wire? You know, the magnetic's going around.
Well, in that one, he's just using his thumb,
It's like,
which is the way we used to do it.
yeah,
Okay,
that's the current flow.
the current flow and then the magnetic field that goes in that
So
direction.
electrostatic field. What's that look? How would you visually represent? Is it,
Well,
is it?
in this next chart over
like-
there,
like-
it's along the line. Normally, it used to show it as radiating out.
So it's
okay.
along the length of the wire.
Now it seems to say that they're going when there's current flow. If it's static, there's no current, no charge flow, it radiates out. It's another one of those magic things. I believe them. I can't disprove it or prove it.
You're a man of faith.
Yes.
And this one.
Oh.
Electrostatic Static would be more.
Yeah, it's just showing the different formulas for the shapes, which is really based on the shape of the object. Okay, so back to our atom. And we got a nice little atom there that's got this valence electron running around. Now I believe they do run around at the speed of light. Very, very, very fast.
Yeah. And how come the outside guy laughing the inside guy?
Well, because this is an old model, and if you look at the Schrodinger quantum model, then you don't have these shells. Things are like a gas all over the place, and probabilities, and makes your head kind of hurt. So we'll keep it simple.
And the Niels Bohr model for that reason.
And assume that just because it's closer doesn't mean it can't travel at the same velocity.
Well, I'm saying that if they were traveling at the same velocity, you'd get more orbits on the inner shell.
Well, you might,
If they're traveling at the same velocity.
but they're also at a lower energy level.
It doesn't change velocity. The
Well,
velocity is c.
I don't know. Does that mean the apparent mass changes? Because E is equal to mc squared. Food for thought.
So if everything's moving at c because it's an electron. Oh, one of them got away.
Yeah, one got away. What happened? It became ionized. Somebody came in and kicked it. It got some UV energy, or it got some photons, or something happened, and it got enough energy to leave.
But it's insecure and came back.
Well, it could. We don't know where it went. It could go out, release photons, come back.
And the AC circuit went that way, then reversed the voltage direction.
Yeah, that's the other thing when we talk about alternating current. Electrons don't go anywhere, they just go back and forth.
Charge moves. Sort of like a dance party.
Okay, so we'll talk a little about voltage. And it's the potential between 2 points when an electric current of 1 amp dissipates 1 watt of power. So think about that a minute. And that's part of the Watt's power law. So it's the difference that will impart 1 joule of energy per coulomb of charge. So every amp second, which would be a coulomb, right? Would be a joule.
I've got too many parameters.
Yeah, I know. It makes your head hurt. But those are the official definitions, been around since these guys invented them, both Volta and Watt or Joule. Watt was involved in this stuff too. He was the steam engine guy and did all the power stuff without all the math. And I'm just showing down here the equivalent between a joule equal to a watt second, and
So Q is what?
Q is coulombs, charge. Charge in coulombs. So if I have a potential difference, like a voltage between 2 points, it creates an electrostatic or E field, we call it, between those 2 points. And that's due to this fact that the positive and negative charges are separated. So the higher the potential, okay, the more force there is to separate charges. But the sum of all of the charges is still going to be zero, at least in this universe. So we use batteries and generators to cause this to happen by generating a force. And in the case of a battery, it's a chemical process dealing with the electrolyte and causing positive ions on one end and negative ions on the other end. And we connect something to that, then we see that potential difference in it. It's sort of, think of it as forcing holes out the positive side and forcing electrons out the negative side. But it's really dealing with charges. And if we have an atom that's missing one of its electrons in a substance like a piece of copper wire or silicon, whatever, we call that missing spot a hole. Okay, and that's a free electron can fill the hole and complete the valence shell on that electron. When it fills the hole, it came from another atom and created a hole. So think about a whole bunch of atoms lined up one next to each other, and I hook up a battery and put a force on there, and I pull an electron out of the first atom and made a hole. Well, the atom next to it, since there's a force from the battery, okay, could create enough energy to cause that electron to move over, be attracted back to the battery and fill the hole. Now I got a hole over here. It appeared to move at the speed of light from one atom to the next. So as I go down that chain, that hole apparently moves. The only thing it moved was electrons going from one atom to another, but the effect of that hole at the speed of light basically moved from one end to the other.
Sounds a little bit like serial monogamy.
And that movement of holes is what we call current flow today, conventional current, which they didn't know about holes back when Benjamin Franklin named it. And he named a bunch of stuff, like positive was charges were positive and negative, and what else did he name? Well, current flow, he decided it went from positive to negative because that's, had to be one or the other. So now when we talk about conventional current flow, we're really talking about the movement of holes and charges moving in the opposite direction. And
did he have a quarter to flip to decide?
I don't know. Maybe he went out and used his kite. Okay, so we talked about the voltage creating a field we call the E field or electrostatic field. And it's going to align itself from the positive to a lesser potential along the surface of a conductor. If I have a strong enough electrostatic field, okay, it can provide enough energy to cause an electron that's in the outer valence shell to get enough energy to leave that atom and migrate to some other atom that's missing an electron. So as those electrons recombine with the holes, okay, and it causes the holes to appear to move, okay, because the electron had extra energy in order to escape or to move. When it was captured or filled in the hole in another atom, it's now at a lower energy level, so it had to release that energy. And it did it as either or a combination of photons and phonons.
Photon
And phonons.
you went on me.
Phonons are lower frequency emanations, and they produce mechanical vibrations and heat. Photons produce light.
So that's sort of like what that gal did in front of the Israeli consulate in Atlanta.
I don't know what she do.
She became a phonon producing light and heat.
Oh, okay. So it's the combination of those which is what dissipates the power. So when we have current going through a resistor, because those atoms require more energy to escape, they're going to release, go back to their normal state. So they're going to release more heat, per se, heat and light, and which is why resistors get hot. And, if you have enough current flow, they'll not only get hot, but they'll generate light and flames. When we have a small amount, like in a semiconductor diode, as it's going between the junctions and losing energy, it's producing mostly photons. So that's why an LED produces light. Turns out any p-n junction produces light. And light on a p-n junction is just the opposite, will cause electrons to move. But we're getting ahead.
Did you ever start the recording?
I thought I did.
Maybe I can't see nice. Oh, I never remember.
Where does it say?
I'm not sure.
Yeah,
Oh,
it said pause, so we must be recording.
okay, good.
Okay. Oh, this one is just showing a standard copper wire with its no charge on it, no voltage. So we have all these atoms and we got free electrons because it's a metal and a very good conductor. Some of those can just kind of leave on their own at room temperature and move around. But there's no net current flow. They don't, migrate to one end or the other. When I apply a voltage, and I corrected these charts because they said current, you have to have a voltage in order to have the current. So when I apply a voltage, okay, now I'm going to take those free electrons and not only add more energy, but I'm going to cause them to flow in one direction, or the charges, basically. So the most common voltage sources that we're going to deal with are batteries or power supplies or household power. In the case of batteries, we have the non-rechargeable carbon, zinc, button cells, things like that, which are just chemical processes. Once the chemical process or the energy is used up, they can't be recharged and they're no longer useful. If it's a rechargeable battery made with different technology, I can put energy back in it, kind of like a capacitor, using it as a storage device. In your house, you have your household power, which the British call mains, which is typically 120 volt AC in the United States. In some cases, you may have 240 for certain devices that take a lot of power. And those all produce a voltage which will create that electrostatic field on the conductors. We normally measure voltage with, the typical thing is a multimeter, and they measure AC and DC volts anywhere from down in the millivolt range up to maybe 1,000 volts. Some of them can measure true RMS, which we'll talk about later, which is the equivalent voltage to DC that would create the same amount of heating. Some will measure the peak-to-peak voltage for an AC circuit, which is as much as 2.8 times the RMS voltage, or the peak voltage. There's, line voltage monitors that sometimes you see that are just there to monitor the AC line voltage to see if it's high or low. In some cases, they may be able to set an alarm on it or something to tell you there's a problem. And then there's laboratory equipment that are very precise, and they can measure down in the microvolts or many thousands of volts. A megger, for instance, measures many thousands of volts to check for insulation and different kind of shorts, things like that. A couple examples. This is the old standard Simpson meter. They're still available, a couple $100 at a Hamfest. This is the new digital Simpson multimeter, available, a couple $100. It does everything the old one does, more accurately. But in some cases where you're doing something, it's advantageous to see the needle move. You can't do that with the digital meter. Okay, so what did we learn? That free electrons is the mechanism to carry elementary charge. And if atoms gain or lose electrons, they're called ions. Oh, cations for the positive, and I think that's the chemical term when it's done in a electrolyte, and an anion for the negative. That voltage or electric potential, or EMF, electromotive force, is the force that causes the elementary charges to move from point to point or atom to atom. We measure voltage in volts, and the most common voltage sources are batteries and household power. And even in amateur radio, most of the transceivers are set to run on 13.8 volts or battery power, whether you're powering it from a battery or an external power supply to simulate a battery. Okay, and what's this one? Oh, current, part of the current wars. Oh, by the way, for people that are interested in history things or physics, there's a great site, and she has a lot of YouTubes, called Kathy Loves Physics. And she does a lot of these videos about the history of all this stuff and how it evolved with all these guys. And it's quite interesting. She does show some math, but it's more about the history and explanation rather than dealing with the equations.
So you're saying that she's obsessed with old dead white guys?
Probably.
Okay.
But they're from all different countries.
Yeah.
We got the French, we got the English, we got the Jewish, wherever they call that from, like Einstein and Oppenheimer and all those Germans, the Ohm, Scotland was Watt, or Faraday was. Coulomb, I think, was French.
Faraday was England.
Was what?
England. England.
But
Oh,
we get to good old Benjamin Franklin, who invented a lot of stuff. He was kind of a unique person. And because I guess nobody else had done it, I mean, he was there when a lot of those early people were around. He named a lot of stuff, maybe because he was a writer. You know, he published, what was it?
Poor Richards.
Poor Richard and a newspaper and stuff like that. So he's the one that named conventional current flow because they didn't know about electrons. And the basic thing about direct current is it always flows in one direction. You can have a thing called pulsating direct current where it goes up and down, but it never crosses zero. It never reverses direction. So if we rectify an alternating current, we get a pulsing DC current. It has the same shape, but it's always either positive or negative.
Always positive or zero. Or
It could be negative zero, but then you have to go to zero. Could have a DC offset. Okay. An alternating current is one that changes direction. And the poor little electrons don't know which way to go. They're back and forth, back and forth.
So the pulsing the DC, that's mainly good for timing functions or?
Well, I don't know. We get rid of it with filters and call it DC. Or if it's the envelope, then we use an envelope detector and say that's the audio. Okay, so current is a measure of the movement of charge. And the free electrons are really the mechanism for moving the charge from one point to another. And the electrons don't necessarily have to keep going in the same direction. I mean, I have an electron in it from an atom, and it moves to another atom. And it could stay there indefinitely. There may not be enough force to cause it to move to another atom. Some other atom has an electron move. So that's why when you calculate like that earlier thing of how fast do electrons actually move, 0.01 millimeters per second is like hardly moving at all.
So electron move, is that like jitterbug or something like that?
The what move?
Electron move?
Yeah. They just jitter all over the place. Okay, so an elementary charge, which we've talked about, and it's a constant, turns out to be the reciprocal of the number of charges in a coulomb, or 1.6 times 10 to the minus 19th coulombs. So if you do 1 over that, you get the 2.5, no, 2.64 times 10 to the 18th. Right, and it's down here. So 1 coulomb per second is 1 ampere per second. And 1 ampere hour is 3,600 coulombs. Oh, I guess I should have deleted that from the other slide. I wondered why I didn't have the title on how fast do they move. How fast do the charges move? Basically at the speed of light. In a conductor, depending on the fields around it and other devices and the material, it's going to move somewhat slower. But I think in anything I've seen, it's at least like 0.6 times the speed of light. And this is just showing typical direct current lighting up a light bulb where you've got electrons flowing through it this direction, or charge really, and conventional current in the opposite direction, which are the holes, which are apparently moving, even though a hole is just an imaginary place for an electron. Okay, the current wars. Thomas Edison not only was sort of the inventor of the light bulb, he was big on direct current, and he invented the dynamo or DC generator. And his goal was to electrify the world with DC. And I think he did most of New Jersey. He had a guy working for him that he hired called Nikola Tesla. Tesla was not so much a DC guy, but alternating current. And the one thing that Tesla really did was get a patent for polyphase power. He eventually left Edison and went to work for George Westinghouse, who was a proponent of alternating current. And he used Tesla's patent for polyphase power for some of his stuff. And he also commissioned Tesla to build a polyphase motor. Tesla never was able to do that. Westinghouse actually wound up hiring some other guy, and I can't remember his name, because he's one of those people that did something and isn't well known for it, who actually made a motor for Westinghouse. But the big thing in all this was alternating current through transformers would allow you to generate power at very high voltages and therefore very low current. So you had much less power loss than you did with direct current. And back in Edison's time, the cost of the power transmission wasn't nearly as much as it was today, because they weren't going the distances. So it eventually turned out that AC power generation took over because of the line losses in trying to do it with direct current. Yeah. Tesla was also off at the time trying to do it wirelessly, which I think he had some experiment which sort of worked, but that was another failed experiment. And he spent a lot of money building these gigantic towers to try to transmit power from one to the other over like a mile. So
now we can go over what, couple hundred feet?
what, power?
Yeah.
I don't know. Go that far?
Yeah.
Really? Okay. But the bottom line in all this was all these companies wound up being absorbed into General Electric, and we use alternating current for power transmission and most motors and things. We measure current with, again, your typical multimeter. Usually they'll go down in the milliamp range and may go up to 20 amps possibly more. Typically, they're limited to around 10 or 20 amps. You may also have like a laboratory ammeter. These also come in a digital version, and they may be a little more accurate. Go down to smaller values. This is just a simple circuit showing an ammeter with a load and some source, in this case, the symbol for a battery, where we're having a current flow. And the conventional current is going to go from positive to negative. The perceived electron flow, which is what they teach in the military, is going to go from negative to positive. The direct current is always going to flow the same direction. We measure it in amps, and an amp is a coulomb per second. Any questions on that one?
Nope. Nope. I'm glad I stuck around though.
Okay. So I didn't confuse you with charges and free electrons and all that stuff.
No, I got it. I thought it was very well explained.
Okay.
I
Does that-
like the little diagram that looked like a string bean with electrons in it. That was that was good.
Yeah, well, I can't take credit for that. I find most of my stuff on the internet. I
I
plagiarize.
guess it looked more like a torpedo tube, but I thought that was a good diagram. And
Okay.
I guess my one big takeaway was I like the idea of the holes moving, and I think that made it kind of clear to me on why it's current goes from the positive to the negative, which it never made any sense to me. And so the
Yeah, well-
holes moving does make sense if I understood that correctly.
When we talk about semiconductors, we'll talk more about holes, as that's
So-
kind of the main thing there. One
Sounds
of
good.
the presentations that you see in a physics class a lot when they do that is they'll take usually it's a clear tube and fill it full of ping pong balls. And they're all adjacent to one another. If you tap the ping pong ball on one end, the one on the other end of the tube pops out instantaneously. So that force that you injected got transferred through every one of those ping pong balls, regardless of how long it is, and came out the other end. That's the way the holes migrate, as those electrons are just going from one atom to the next, but the charge is moving along, filling in the apparent holes. That's kind of a neat thing, but it's kind of hard to demonstrate on Zoom. Maybe I could. I got another camera I have to try sometime.
Well, I